Okay, so very quickly I just want to walk you through this little derivation. There's not that much to it, but the idea is that if you have, I'll draw, if you have an axis, do this in a better color, you have some object and it's rotating around an axis, then its angular velocity, how many radians per second, is related to its actual velocity by the fact that, well, you know what the radius is. Okay. All right. So the only thing is that if you have a thing, if you have some sort of a solid here, this little chunk there, it's got a smaller radius than this little chunk there. Right? They might have the same angular velocity. Well, if this thing is rotating around, they have the same angular velocity. But one of them is actually moving faster, and even though they're the same little pieces of mass, one of them has more kinetic energy. Right? So if you want to compute the grand total amount of kinetic energy, you just have to add up all these little bitty pieces of kinetic energy. And for each one, the kinetic energy is 1/2 mv squared. M being the amount of mass in that little chunk, which is therefore the differential dm. Does that make sense? Mm-hmm. Yeah. Okay. So, well, then don't forget that V is Rw, and I can't believe I just said W. It's omega. Omega is a constant, so it factors out. 1/2 is a constant, so it factors out. And what you're left with is, weirdly, that kinetic energy is 1/2 of this thing times omega squared. And what's weird is the usual formula for kinetic energy is 1/2 mass velocity squared. So this is 1/2 of question mark times angular velocity squared. So this is basically saying that you can, if you have angular motion and if you know the angular velocity, then this thing here is sort of the angular analog of mass. Right? So a moment of inertia is all that is. It's just the angular analog of mass. I don't know why I erased that. Okay, so I just think it's healthy for students to know where these things come from. In other words, this little formula here, integral r squared dm, doesn't just come out of thin air. Okay. All right, and of course dm is density dv. It's just kind of an easy way to write that down. Okay. All right, so what the question is actually asking us to do is to actually compute the moment of inertia. So we're going to just plug and chug here. And the specifics are that we're rotating around the z-axis. Of course, you have to know what you're rotating around to understand the motion. This is the domain. And we've got this density function. So let's draw a picture. Let's see, the box was, yeah, it's the unit box. So there's our box. It's rotating around the z-axis. Okay, now you'll recall that in this little calculation we just did, this r that came up, r is the distance to the axis of rotation. Right? So now that we know what our axis of rotation is here, we've got to ask, given some arbitrary point, over here, x, y, z, what is this distance to the axis of rotation, that axis being the z-axis? Does that make sense? Mm-hmm. Okay. Conveniently, that distance is the same as this distance, and that being x and that being y, our r is the square root of x squared plus y squared. Now that's a coincidence. It happens to be our polar r. Right? In general, it might not be. It depends very much on what the axis is. Okay. All right. So let's see. We're interested in computing integral r squared dm. So that means we need to do integral, well, let's see, r squared is x squared plus y squared. Yeah. dm is density times dv. dv is dx, dy, dz. Conveniently, this domain is a box, and so they all go from 0 to 1. And density was given, even though I've forgotten. Let's see, density is x squared plus y squared plus z squared. Okay, all right, well, I didn't leave myself much room there. So that's our r squared, and that's our delta, and that's our dv. And plug and chug.
Okay.
Happy?
Mm-hmm.
Okay. All right, let me stop the...
Are there